Hello, this is the first video in the Graph to Network 2 series for OCR Discrete Further Maths. It looks at finding a minimum spanning tree using Prim's algorithm. As a reminder from previous videos, a spanning tree is a graph that connects all of the vertices but has no cycles, so no closed paths. If we have a graph, we can select a subgraph but is a spanning tree. There may be more than one possible spanning tree. Let's look as an example at this network here. There may be more than one possible tree. We want the one with the minimum total weight or length. As you can see in this example here, we have connected R to S and R to C and then R to W and W to L. We have a total length or weight of 43. In this example here, we have gone from R to C to S to W to L. And we can see that this wouldn't give us as lower weight as the previous spanning tree. For small networks, it might be possible to keep on looking at all the different spanning trees and to find the minimum by inspection. However, for larger networks, this would be quite impractical, and we might need a computer to help us. Therefore, we need an algorithm that will find a minimum spanning tree for us. One such algorithm is now known as Prim's algorithm and was actually developed in 1930 by a Czech mathematician, but later rediscovered and republished by computer scientist Robert C. Prim in 1957. This is the algorithm we're going to look at in this video. So here is Prim's algorithm written in terms of steps in English. Step 1 says select any vertex. However, do be careful to read the question, as sometimes the starting vertex is given there. Step 2, we select the shortest edge connected to that vertex. Step 3, we then select the shortest edge connected to any of the vertexes already connected. So you are building the spanning tree in a connected way. Step 4, repeat step 3 until all vertices have been connected, and then stop. Let's try it with this example. I'm going to choose to start at the vertex C. The shortest arc coming out of C is CL, which is of length 7. And I'm going to start to draw it as I go as well. Now I can look at any arc coming out of C or out of L, and I choose the shortest. The shortest is LW at 5. Now I can choose any arc coming out of C, L or W, as long as I don't create a loop, a closed path. So for example, I can't choose CW because that would create a path between C, L and W and back to C again. So the next shortest one is one of the 12s, so either CS or CR. It doesn't really matter which one of these I choose. I'm going to decide, I've chosen to go for S, but you can see therefore there would be more than one minimum spanning tree in this example. And then finally I have to go from S to R, and that then completes the minimum spanning tree. To add all those up, I find I have a total weight of 35. It's really important that you list the order of the arcs as you're choosing them as you go along, that you remember to calculate the total weight of the MST, and that you do draw the spanning tree as well. So what would happen if I start at a different vertice? Well, I should get the same minimum spanning tree in terms of weight, but obviously the order of the arcs I choose will be different. What happens if more than one edge could be chosen? For example, here I could have chosen CR instead of CS, which would in weight 12. I would have still had RS at the end. I would have still ended up with the same MST in terms of what it looks like, but the order of the arcs would be different. In terms of an exam question in the marking guide, the examiner would give you marks for either one or other of the MSTs if you have a situation when more than one edge can be chosen. For this second example, you may wish to pause the video and try it for yourselves, or you may wish to check starting at a different vertex later. As you're working through, do remember in step 3 to keep looking at all of the nodes you have already connected. Working through the second example then, I'm going to choose to start at A. If I look at A, I have a choice between 30 and 31, so I'm going to choose the shortest one, which is AC at 30. I'll just, at the moment, do it over on the diagram to give myself more room. Therefore, I can now choose any of the arcs from 31, 22, 24 or 29. The shortest of these is CD at 22. From there, I can choose any of the arcs coming out of A, D or C, and the shortest of these happens to be DE at 18. When I say any of the arcs, I have to be careful not to create a closed path, of course. From here, I have choices. I could go from D to B and with 24, I could do CE at 24. But I can't, because actually what I've forgotten to do in this diagram is that I've already joined E to the network. So drawing the network as you go along really helps you make these mistakes. So DB at 24 gets added. From here, I am looking around again for the next shortest, and I can see that EG is a possibility at 26. Now I just have to connect F and H. And I can see that FG at 21 is how I'm going to join F, and then with H I choose the smallest way of joining that, which is GH. So hopefully you can see the minimum spanning tree diagram in blue drawn on top of the other one. And if I was to add all of those numbers up, I would get 174 as the weight of my minimum spanning tree. So let's just look at some of the common errors or the mistakes you potentially could make in applying this method. Well, a common one is not reading the question. If it tells you to start a specific node or vertex, then obviously you need to start there. Some people do not choose the shortest arc to add. Some people form a closed path or a cycle by accident, or don't check that no cycles have been formed. Some people do not look at all the connected vertices when looking for the next edge, and therefore don't choose the shortest arc possible. Some people forget to record the order of the arcs as they go along, and then at the end they write them down in the wrong order. Some people don't do that at all and don't show enough working and lose marks that way. Or at the end they lose a mark by forgetting to state the length and weight of the MST. In the next video, 2.2, we'll be looking at finding an MST by Prim's algorithm again, but using a table rather than network.